So the material that I'm presenting today is actually a series of notes. The reading that you had ahead of time was all kind of from the first chapter of a monograph that I'm at very early stages on. And this is building out three of the main philosophical themes from that material. So before I get into the details and what we're going to see, I want to say some very broad-based stuff about how I think about philosophy of physics. So I know most of the other presenters in the summer school have been space-time people, space and/or time people. I am a matter person, and I am very specifically a condensed matter person. So I don't really think about exotic high-energy matter. I think about condensed matter, and I like that better as a way of framing my research as opposed to whether I'm chemistry or physics or both or neither, because nanoscience is all of those things, but it is in almost all cases condensed matter. So I'm motivated by thinking about condensed matter. I like condensed matter. I think there are good reasons to think about condensed matter as philosophers of physics, because it makes up a lot of physics and it makes up relatively little philosophy of physics. And there are good historical reasons for that, especially if you look at how philosophy of physics came around in response to the new quantum theory and the special general theories of relativity in the early parts of the 20th century. We can kind of see how the trajectory went that way, but there's so much physics that's condensed matter, and I want more philosophy of physics to be centered around condensed matter. So that's why I like thinking in that space. It's also the case that condensed matter unites chemistry and physics in some interesting ways and gives us new strategies for thinking about how those two branches of science can talk to one another. So yay condensed matter in general. Nano, which nanoscience and nanomaterials are my main bread and butter. Nano is a new and difficult and very pervasive form of condensed matter. It's a technology that's sort of showing up all over. Some of you may be looking at nanoparticles on your screens right now, depending on what kind of computer you have and how fancy it is. And I think it's a technology that we're going to have to reckon with in more widespread terms, which is why I'm trying to do some philosophy on it. Okay, additional sort of orientations toward how I think about philosophy of physics and philosophy of science. I tend to do science first philosophy of physics, and you'll see that very much here today. Most of what I'm doing in the lecture slides is just talking through some science. And I would love feedback. I know I said this in the readings on the summer school reading packet, but I would love feedback on what parts of the science you want more on, what parts of the science are too bogged down in the details. Like I said, this is material that's going to be forming a monograph, and I'm still trying to get the narrative right. And so this is a sort of, you're a test audience for me. And if you want to send me an email afterward and let me know any thoughts you have on that, that'd be great. What I mean by science first philosophy of physics is I'm going to show you some science and we're going to do some philosophy about it. That is different than philosophy as continuous with physics, which you see a lot in foundations of physics circles. Some of our organizers work in those circles. I think that's an important way of engaging philosophy and physics together. And I also think it's distinct from the kinds of things that I do, which is using kind of old school conceptual analysis techniques to think about what's going on in certain areas of nanoscience. I also think it's important to do philosophy of science for science. Again, this isn't what everyone has to do, but it is what I do and what I like doing. What I mean by that is that I want the results of my philosophical research to be useful for science, to serve science, sometimes more than I want them to serve philosophy. And that sometimes gets me into trouble when I try to talk to generalist philosophical audiences and they keep asking me who cares. And I say, well, scientists care, and that's why I care. But what that means practically is that I want to think about what philosophy can contribute to scientific research. And so a thing that philosophy does well that I alluded to before is conceptual analysis. And I think that's something that we get to do as philosophers better than physicists, or better than a lot of physicists. And so that's where I anchor a lot of my philosophical work. I also think this is partially personal preference, partially what I've seen work when I talk to scientists about philosophy of science. I tend to find that epistemic results from epistemology tend to make more of a difference for science than results from metaphysics. That's not to say that metaphysics isn't an important domain of research, but I think a lot of the metaphysical results that we get in philosophy of science are more important to philosophy than they are to the sort of day-to-day practice of science. And I imagine there are folks on this call who want to fight me on that already, and I look forward to doing that later if you're interested. Okay, so that's just broad-based background. The game plan for today, like I said, there's going to be a lecture-y bit on the science of quantum dots. I've got 3 parts of quantum dot science that I want to talk through. The first is semiconductor physics. The second is just a little bit on alloys and alloying and how we think about alloys at the nanoscale. And the third is the procedures of noble metal nanosynthesis, which is the making of the quantum dots. Throughout this, feel free to interrupt with questions and clarifications. If you're feeling bold and brave, you are welcome to unmute your mic and try to shout me down. If you are feeling less brave, type something in the chat window and I will look for it. And if I don't see it, I imagine one of our organizers will, and they can be brave for you. Okay. After we get through a bunch of science, I want to do a quick overview of some of the discussion options that I want to give you for the second half of our time together. Here's what they are. I'm not going to read through them now. You'll see them in the poll options later. We'll take a quick break, and then during the break, you'll vote on what things you want to discuss, and then we will discuss things, and then we will be done. That's my plan. So let's get into it. Quantum dots. Here are 2 pictures of quantum dots. The first is a picture of a bunch of quantum dots in a colloid. The second is a picture of the sort of hypothetical structure of a particular kind of quantum dot. Quantum dots are semiconducting nanoparticles with tunable quantized band gaps. That's what's interesting about them. They do some cool physics that other materials don't. In particular, they exhibit this thing called quantum confinement, which you shouldn't already know what it is unless you read the notes very carefully ahead of time. We're going to talk through what that is. They have a nickname, the artificial atom. These are nanoscale materials. So a nanometer is a billionth of a meter, about 1/200th of the width of a human hair. So teeny tiny things, but not the teeniest, tiniest things. They are larger than individual atoms, larger than a lot of molecules. As you can see in the representation on the bottom figure there are a bunch of atoms that are stuck in there, and a bunch of atoms that are not part of the nanoparticle that are in the nanoparticle as well. So all of the sort of white dandelion puffs on the outside of the nanoparticle in the bottom figure are not actually part of the particle. They are there to stabilize and hold the particle in place. But these particular brand of nanoparticles, quantum dots, are designed in order to do some really cool physics at the quantum classical interface, where you can get quantum effects in larger scale materials, bigger materials than we typically see quantum effects in. So I'll be talking about that in a little bit. I just want to highlight that that's part of what's going on there. I just got a chat. Is that true? Something happened. Yes, but my cursor is going. Well, we can talk about that for sure in the discussion, Keith. Keith's just asking about whether we want to talk about whether epistemology is better than metaphysics. Okay, back to quantum dots. There are applications of quantum dots across a lot of technologies that we see today, including solar cells, LED displays. So if anyone has enough money to be going out and buying televisions these days, congratulations, I suppose. QLED TVs, QLED TVs are televisions with LED displays that have quantum dots in there. They give us very bright and highly tunable colors. Also, if you're a gamer and you have a gaming monitor, QLEDs show up in gaming monitors as well. In medical imaging, we see quantum dots used, and especially integrated circuits. Integrated circuits are important. They are the things that make most of our electronics go. And integrated circuits are part of the reason that we're interested in the semiconducting properties of quantum dots in particular. They're also useful for catalysis, industrial catalysis. We're always looking for more efficient ways to catalyze chemical reactions. Okay, so big takeaways, quantum dots, they do this really cool, bright, shiny thing. That is the quantum confinement phenomenon that you're seeing in the bright display of the jars of liquid up top there. It is a result of a particular kind of semiconducting. So quantum confinement comes from the general semiconducting properties of the quantum dots. We'll talk about that in just a second. A teeny tiny bit of history first. So way back in the 700s, Geber, also known as Jabir ibn Hayyan, created a bunch of formulae for different proportions of metals that produce different colors of stained glass. This is Geber. He's often known as the father of chemistry. And it's kind of interesting to me to know that this guy who was a chemist is working in stained glass colors at around the same time that Islamic optics are really taking over the intellectual world. Islamic optics affected a lot of the ways that we built our optical theories through the last millennium or so, and as you'll hopefully pick up on, quantum dots are right at that interface of chemistry and some interesting optical phenomena. So this is kind of all coming back a millennium and change later. Relevant for us right now, stained glass produces colors. A lot of stained glass produces colors via a different nanoscale phenomenon called localized surface plasmon resonance. Basically, you grind up metal powder really fine, you stick it in molten glass, and something happens, and you get this surface plasmon resonance, which is not the same thing as quantum confinement, but is another behavior of nanoscale materials that sits right at the classical quantum interface that I'm interested in. So there we get stained glass. This is from the Prague Castle, and the red in there is from tiny bits of gold. The blue in there is probably from cobalt, possibly from silver, depending on how they were mixing it. Okay, jumping forward a millennium and change, in the 1950s to the 2000s, there's a lot of material science research on surface chemistry and on semiconductors in search of better material for integrated circuits, which are computer chips, right? We got interested in making computers better once we figured out how to make computers. And this was where a lot of Bell Labs energy took off in the latter half of the 20th century. In the mid-1970s to 1980, a Russian physicist and chemist named Alexei Ekimov produced some molten metal nanoscale mixed metal nanoscale particles stuck in a molten glass matrix. So he was actually using that same molten glass technology to trap the metals that we used from stained glass ages and ages ago. Here's some of the fluorescence spectra from the Ekimov paper. It's in Cyrillic, so I can't tell you what it says because I don't read Cyrillic. But it's a sort of typical looking, interesting fluorescence spectrum, especially because the peaks are so narrow and so intense. So this is part of what's exciting about what quantum dots can do, is they can give us really intense narrow peaks. The problem with the Ekimov particles is that they're trapped in molten glass, so it's hard to put them into the integrated circuits that we want to put them into. So in 1982, we get first the sort of theoretical foundations for what's going on that gives us that kind of fluorescent peak from another Russian chemist, Alexander Efros, and he postulates quantum confinement, which we'll talk about in a second. And then in 83, an American chemist named Louis Bruce produces the first colloidal quantum dots. So quantum dots in our colloidal liquid form. They're cadmium sulfide dots. There are a bunch of different alloys that get used to produce our early quantum dots. And after they get the first colloidal quantum dots, there's just a ton of work on making them better. So there's work on monodispersity, which is the problem of how to make them all the same size. The work on different kinds of architectures, different internal structures for quantum dots, on tuning the emissions that you get out of the quantum confinement response, so on and so forth. I believe alongside my notes on quantum dots, I sent around a review on synthesis of quantum dots from, from Paul Olivisatos, who's another chemist who was working on some of the early work on quantum dots. And he talks about all of the work that happened sort of from the 1990s forward. So if you want more details on that, that's a great review. Okay, I've been teasing it. Now let's get into the actual physics. So talking about semiconductors first. The important things to know about semiconductors are how the bulk and the band gap work together. So we're going to be talking about bulk semiconductors on this slide. The band gap in semiconductors is just the energy required to move valence electrons, the surface layer electrons, from their sort of resting state to the conduction band, which is an energized state. It's analogous, for those of you, and this is for my old buddy Josh Hunt, who came to us from chemistry, analogous to the HOMO-LUMO gap in molecular theory. So here's a typical diagram, schematic diagram of how we think about where electrons live in molecules and in solids. Over on the left side, you have your HOMO-LUMO gap. These are molecular orbitals. The highest occupied molecular orbital is the lower one. The lowest unoccupied molecular orbital is the higher one. And if you remember your freshman chemistry, you might remember having to draw arrows to put the electrons in different orbitals. That's when you have a single atom. When you have a solid, all of the different HOMOs and LUMOs sort of overlap with one another. And rather than just having a single energy level, you have a band of allowable energy levels, which is where you get the band structure discussions of how solids distribute electrons. And then you get this thing called a band gap, which shows up in semiconductors. And the band gap is analogous to the energetic gap between the HOMO and LUMO, in the sense that you're not going to find electrons at that energy, at any of those energies, either in between the HOMO and the LUMO in a molecular solid, or in the band gap within a semiconductor. So in semiconductors, you have a valence band, you have a gap, you have a conduction band. Not all materials are like this. Here we go. Sorry, I had to skip forward to get my, my second visual. Metals in particular, you can see on the bottom picture there, there's overlap between our valence and our conduction bands. That's why electrons flow so freely in metals. That's why they conduct so well. Semiconductors, as you might guess from the name on the packaging, semi-conduct. They conduct better than insulators, not as well as metals. And it's because of this band gap, because there is an energetic barrier to excitation into the conduction band, but it's surmountable. Whereas in a good insulator, the conduction band is just going to be too far away to get to. So bulk semiconductors are materials with small but non-zero band gaps. Our elemental semiconductors, silicon is the main one. Silicon, as you may know, is also the thing that we use to make computer chips. Semiconductors and computer chips are friends. We also have germanium as another elemental semiconductor, and there are a bunch of alloy ones that we'll talk about in a minute. Semiconductors are essential to diodes and transistors, and here I like to use an analogy of semiconductors being the kind of surface streets as opposed for electrons, as opposed to metals being the highways for electrons. So you can get a lot of electrons moving very fast, easily down a down a metallic surface, whereas in a semiconductor, you have a more gated structure. So you have better control as you have less flow. Tuning the band gap, which is one of the big things that we try and do in both bulk and nanoscale semiconductor science, is your way of gating the traffic flow. And here, to pull it out of the analogy, what you're doing when you're gating the traffic flow, they actually do use the language of gates when you're building diodes and transistors, but you are converting currents and stepping up and down voltages and redirecting electron flow from one part of an electronic circuit to another. So tuning is a really important way of making sure that we are getting the right kinds of currents in the right kinds of places, not too much, not too little, so that your computer works and doesn't either lose power or explode. And so it's an important part of electronics. And tuning has a lower bound, which is the band gap itself. You can't tune so much to get that you can put an electron in the middle of the band gap. The band gap is the kind of lower bound of what you can tune to. So the movement of an individual electron across the band gap is the most precise movement that you can expect out of a semiconductor. And that is a fairly theoretical expectation at this point. There are certain quantum dots that are letting us get at individual excitations, but in general, we're looking at numerous electrons moving across the band gap at once. I'm going to come to particle in a box on the next slide. Okay, so ways that we think about how semiconductors work. One of the reasons that semiconductors work at all is because they create these things called excitons. Excitons are excited electrons, so electrons up in the conduction band, paired with holes, the gap that was left behind by the electron as it was excited. So this is a sort of semi-classical spatial analogy to what's going on, and then electrons and holes get bound together in order to form excitons, and they are bound together by electrostatics. Again, a fairly classical theory of what's going on as we get electrons promoted to the conduction band. So I've said these things. The reason we get a bound exciton state is that your positively charged hole attracts your negatively charged electron via classical electrostatics, which gives you this quasi-particle, the exciton. Excitons are important to the story I'm telling here because they have sizes. So the size of an exciton, the spatial extent of an exciton is called its Bohr radius, its exciton Bohr radius, not to be confused with atomic Bohr radius. And the exciton Bohr radius of most materials, it's a material property, so your exciton Bohr radius for silicon is going to be slightly different than your exciton Bohr radius for cad selenium, but it's going to be dependent on the nature of the material and on the band gap. So the exciton Bohr radius happens to be in the nanoscale. Just kind of so happens, this is a material fact about nature. And what that means is that you can see in the diagram up top here, so the diagram, I should explain, your grayed out areas, the big grayed out circles, are the spatial extent of the exciton. You can see one has a large exciton Bohr radius, the other has a small exciton Bohr radius. And what you want to be visualizing is these are sitting on top of on the surface of a lattice that's pointing into the screen in the z direction. In bulk semiconductors, excitons move around. They move across the surface, and they're fascinating from a sort of greater condensed matter physics standpoint because they are energetic carriers without being net charge carriers. So you can move energy around in the semiconductor without transmitting net charge. Excitons are also quasi-particles in the way that, well, we see a lot of surface physics and thermophysics likes playing with quasi-particles as well. Okay, for our purposes though, to get us into the nanoscale, our exciton Bohr radius happens to be in the nanoscale, so instead of traveling all over the material, transporting energy without transporting net charge, we get localized excitons at the nanoscale. And our localized excitons happen to allow us to produce this thing called quantum confinement. So quantum confinement is a kind of macroscopic analog to the old quantum mechanics theoretical particle in a box problem. So particle in a box comes from the wave-particle duality. We think about a particle can move at any speed, and that's what's shown in our A box here. But standing waves can only be produced at certain wavelengths, and we're getting B through F show us our appropriate wavelengths. This is where we get the quantized energy that leads to exactly the kind of HOMO-LUMO gaps that we were talking about earlier. I know that we've got a range of people with different backgrounds in physics, so I'm not going to go into particle in a box any more sort of detailed than that right now. This GIF that you're looking at is just from the Wikipedia on particle in a box, and if you're feeling like you need to know more about particle in a box than what this GIF and what I have told you, just Google it for now. If you've survived this long in the summer school, you can probably make it through the Wikipedia article. What I want to focus on here is that what we get is, through the localization of excitons, is a particle in a box like effect, where by trapping the excitons, we force the exciton to behave like a wave rather than like a particle, so that we get these permitted and non-permitted energetic levels, which allows us to get that more fine-grained tuning of energy levels in our conduction bands. Okay. So now we've gotten all the way back around to quantum dots. I've already told you that the quantum confinement generates a, well, I didn't actually tell you it generates a splitting of the bands. I'll give you a visual for this. So in our semiconductors, we have that one band gap, and then we have a bunch of continuously permissible states on either side of it. When we move into quantum confinement, because of particle in a box like effects, we get to see actual splitting of the energy levels so that it's a quantized jump from each energy level. There are more permissible levels than an individual molecule where you have a single HOMO-LUMO gap, but fewer than a bulk semiconductor. And that's what allows us to compress our emission peaks and see more intense and more finely tunable ranges of emission. So to translate that into kind of tech speak, that's what gives us the super bright colors on the QLED TV.
Julia, clarificatory question.
Sure.
What is N in this chart?
Sorry, that's the,
what are we tracking?
Yeah, no, that's the number of atoms, the number of atomic orbitals. Yeah. Okay,
and in the center of the quantum dot, this would be?
Just in a material. So this is all within a material. So if you have so like the HOMO-LUMO gap is being presented for a diatom for a 2 atomic center molecule. N equals 10 is there are 10 atoms in that cluster. N equals 2000, that's a 2000 atom cluster.
Thanks.
Sure, good question. So like I said, that gives us brighter, more controllable colors. It also gives us more precise transistors for integrated circuits. Here's a visual with slightly more color showing more or less the same thing. This visual is fully within the band gap conception of quantum dots, so we don't have, you can actually, well, I guess you can see a little bit of the splitting. And it's giving us a narrowing of the exciton Bohr radius, which gives us a green shift and then a blue shift into the emission spectrum that's being produced by the quantum dot. So here you'll notice, or maybe if you're not noticing, I will tell you, the x-axis is flipped, so decreasing size goes to the right here, whereas decreasing size goes to the left on the top diagram. Okay. So that's the big cool thing that quantum dots do, and this idea of quantum confinement is why people are so interested in making quantum dots. There's also another thing that quantum dots do that shows up in philosophy of physics in other places. And since I know at least one of the reading groups was doing a bunch of stuff with Elisa Bakalich's work, I do want to highlight, since she's talked about quantum dots as well, there's another thing that happens in quantum dots, which is quantized conductance. So this is Coulomb blockades. You see the violation of Ohm's law, which I think shows up in Bakalich's work. So if you're familiar with her research, she did a sort of famous example on stadium quantum dots, where she has classical orbits in a quantum dot that she's looking at. This is the can classical something explain quantum phenomena. Can classical physics explain quantum phenomena, which shows up in the book as well that some of you were reading in the reading group. So the actual stadium example that she's talking about there, the orbitals that she's talking about there, are in a quantum dot, and a theoretical quantum dot. So this is all to say that this is a sort of larger example of electronic theory at the classical quantum interface that presents some interesting philosophical challenges. Elisa's work has addressed some of it. When I've worked on surface plasmons and some of my other work, I've talked about additional phenomena that we see at the classical quantum interface from nanomaterials research. And in the upcoming book project, what I'm hoping to do is get more into how nanoscience sort of gives us puzzles for electronic theory at the classical quantum interface through semi-classical physics. Okay, so that's the end of semiconductors. Alloys and synthesis are going to go faster. So alloys are old technologies that present new challenges. I believe I've said by now, and I'll say it again, we are trying to make quantum dots out of alloys, and that's why alloys are relevant here. Alloys come to us from the Bronze Age, right? We have mixing metal, and this is like the Google image that shows up for Bronze Age smelting. It's the only one I could find. I don't know who the artist is. But you know, we have the Bronze Age, which was mixing of metal that fundamentally changed human society. And it's probably an overstatement to say that mixing metal on the nanoscale is going to change human society all over again. But we do have really cool integrated circuits that we didn't have, 75 years ago, that are letting us survive this present pandemic in interesting new ways, like live streaming philosophy of physics lectures onto YouTube. So I think it's just worth pointing out the historical connection here. Bulk alloys, what I mean by alloys are just metal mixtures in a solid solution. They are not molecularly arranged with one another. So this isn't a metal compound. This is metals that are mixed together, usually by heating them up, like in this Bronze Age lithograph or line drawing. And they form a variety of structures across a variety of scales. So I'm actually going to poach from myself. This is from a different talk on alloying, just to give you a sense of the different varieties of structure across scales in alloys. So starting at the bottom, we know that there are different allotropes of iron that comprise steel. This is all about steel. But if we build from the bottom up, we have different ways that iron can be arranged in order to make the iron bits of steel, different allotropes of iron, different arrangements of iron at the atomic level. those different arrangements can in turn be built into different kinds of microscopic structures. We call these grains, and different grain structures lead to different material properties. So in steel, there are plenty of names for all of the different grain structures: bainite, martensite, austenite, ferrite. They all have to do with both the distribution of iron and carbon relative to one another and the arrangement of them in terms of the size of grains, the orientation of grains, the relative proportions of iron and carbon. And then we can move up another scale into the sort of mesoscale structure of how we fold the grains together. So here you can see in the meso 1 grain structure, there are a bunch of different ways that grains can be combined. And if you've ever spent too much time watching YouTube videos of people making knives, which I recommend as a recreation, it's pretty cool. If you see them like folding and beating the steel until ripples form, that's changing the grain structure of steel, which again changes the material properties. All the way out to the macro scale, we get large scale sort of continuum descriptions of what's going on with steel. You have steel that has a melting point, an elastic modulus, a hardness. In other work, I argue that that kind of property only exists at the macro scale, and you can't kind of get things like melting point and elastic modulus out of just the microstructure. I think that's an interesting reason not to get too hung up on reductionism and emergence, which we can potentially talk about later if other people want to. Okay, so that's just a kind of side note to give you a sense of how complicated alloys are structurally, and that they are not simple molecules, right? They're not things that have regular regular chemical formulae that you could write out. It's also worth noting that in your typical sort of industrial steel, you can have an island of iron or an island of carbon, a grain of iron, a grain of carbon that is a few hundred nanometers long. And depending on your steel, that's a totally normal distribution of the different component elements. That's important because when we zoom down to the nanoscale, if you have a 500 nanometer long island of something, then you just have that thing, right? 500 nanometer long island of carbon is not a nano cluster concept, right? Okay, so coming back to our original slide, I've said this plenty of times now, semiconductor fabrication, all quantum dot fabrication happens via alloying. And what I'm interested in this part of the talk is just what that could even mean at the nanoscale. Like, what does alloying mean for nanomaterials? So when we look at this conceptual diagram that I showed all the way at the beginning, what you see is a highly regimented arrangement of individual atoms of different identities. So our blue is cadmium, red here could be selenium, could be sulfur, zinc or cadmium are yellow, and then sulfur or selenium are the green. So whichever one is not in one, it's in the other. And what they're trying to depict here is a way of building not only two alloy mixtures, but a relationship between the alloy mixtures. So this is what's called a core shell architecture. And it's an important architecture for the building of quantum dots in order to continue to refine and precisify the quantum confinement effects that they're able to produce. Okay, so nanoscale alloys don't have grains in the classical sense because grain structure just can't be downscaled, but they have individual atoms that can affect the entire electronic structure. So in some computational work that was done, 6 or 8 years ago now, the group that I worked with back in grad school built these schematics of gold copper clusters where you have a single copper that's the sort of blue thing in the top there, that gets embedded into different clusters and gets placed. You don't see it in this don't think you see it in this diagram, but it gets placed in different parts of the cluster. And by moving it from the center to one of the edges of the cluster, you can change the electronic properties of the copper cluster in ways that are analogous to doping a metal with an exotic transition metal or an exotic metal species in order to change the material properties of the alloys. So I've built an argument elsewhere that means that individual atoms behave like grains. That's still work that's in progress in various ways, and that I'm kind of shopping around as I'm thinking about what the concept of an alloy means to the nanoscale and how, and I think this is the important question to answer for that line of research, which is how do we transfer all of the good stuff about alloys into the nanoscale, right? So all of our theorizing about how grains mix and how that's different from molecular chemistry of metals, how we can have a mesoscale approach to understanding and modeling alloy materials that's different from our kind of macroscopic homogeneous understanding of it, and also different from our microscale understanding of alloy structures that tell us about a lot of the relevant material properties that we're interested in. So that's the kind of question, if we want to go down the alloy route, that's our second discussion option coming down the pike. Last bit of science, synthesis, how these quantum dots get made. Here's how. So this is a fairly standard schematic for a synthesis procedure, and I know it's a bit small. I can post this afterward to the summer school if you're interested in looking at it, but if you Google colloidal nanoparticle synthesis, you'll get a bunch of schematics that look more or less like this. And they all start in the very first image here with colloidal synthesis. Is there a way? I know I lose my cursor when I present, but I'm going to see if I can annotate here. Is this working? Okay. It is, but I don't know how to clear it. This might be ill-fated. So in the first step here, can you guys see that circle? Does this help? Should I abandon drawing on it? Okay, I'm going to keep drawing on it. I'm getting a couple nods. So our first step here is actually representing a standard chemical colloidal synthesis. So what they're saying in the growth solution is all of the different chemical precursors. So this is your kind of cartoon chemistry as, you know, dumping bottles of stuff into other bottles of stuff. A picture of what happens in the chemistry lab. And that's the very first step in a nanoparticle synthesis. And all of that requires its own kind of chemical theory in order to understand how to grow colloids. But as soon as this first step is done, and let me see if I can get out of annotating. This is going to be tricky. I don't know how they haven't solved the problem of your cursor goes away when you're in presenter view yet. Does this work? Okay, yeah, I think we're back on track. Okay, so within that bottle of stuff, you have all of the theory of chemical colloidal synthesis that goes into beginning this reaction. However, as soon as you move past that first step, they start to reconceive of the way the synthesis goes in a way that's much less chemical and more kind of dependent on the notions of phase change that we see in more kind of physical approaches to condensed matter. So I'm not going to walk you through the whole synthesis, but there is typically in a lot of noble metal nanoparticle synthesis, you start with a seed and you grow the seed in one pot, and then you put it in a growth solution in another pot. The reason you want to do this is that monodispersity thing that I referred to earlier. I'm going to build out this slide because I think I'm kind of talking all over the slide right now. Nope. Um, so nanomaterials don't want to stay at the nanoscale. They want to either break up into their individual atomic components or grow out into the bulk. The nanoscale is really energetically unfavorable. And in order to keep things at the nanoscale, that's why we have to do all of the remaining 11 steps of this sort of typical synthesis procedure that's described here. There are also a lot of models of growth that are used in order to try and explain the nanoscale, the nanomaterials growth problem. So this is a depiction of Lemaire's model of growth, which shows what happens when you introduce growth solution at different points in time, or when you move in and out of nucleation phase at different points of time. Nucleation is the same as your sort of seed phase. So the typical procedure that's depicted up top is going to start a seed solution, which is your nucleation solution, and then get put into other solutions in order to grow. You want to keep that nucleation era as short as possible, so that you don't have something that's nucleating at t equals 0 and something that's nucleating at t equals 10 and something that's nucleating at t equals 100. Because by the time something's at t equals 100 and nucleating a new particle, the thing that started at t equals 0 has already been growing for, you know, your 100 time step units. And so it's going to be a very different size than the thing that nucleates at t equals 100. So you want to keep the time window really small on your nucleation process. And that's actually what's depicted in this model here. As you can see, when there are larger windows of nucleation, so that that more distributed curve that's associated with the sort of medium line, not the thickest line or the thinnest or the dotted line, but in that medium line, you have a mixture of smaller and larger particles, which is bad because different sizes of particles are going to give you different quantum confinement effects and all of the other different effects that you don't want in nano. But like I said, you want to try and keep everything the same size and the same shape in nano, and that's one of the real practical challenges of nanoscience, is you can't just kind of carve down the spheres into your preferred shape, because they're tiny and you can't, without atomic force microscopes, like actually remove individual atoms off things. That's just not a practical way of building your materials. That's all the monodispersity problem. So that's this graph, which shows up in the summer school notes, is one way of representing it. Here's another, just a series of microscope images that show you different levels of monodispersity. So if we look at D, that's actually a fairly typical. You get a mixture of a couple different kinds of sizes and shapes. They're doing pretty well at getting their more spheroid particles all relatively the same size. But you should be able to see in D there that they've got a couple rods, they've got a couple triangular prisms kind of around the center there. And those are all going to produce different optical and electronic effects than the spheroids. So C is a really nice growth of rods, where it's almost entirely rods. You can see there are a couple spheres here and there. And the rods are all more or less the same size, whereas it might be a little hard to see. You might have to like get close to your monitor and squint. In B, there are rods of much more varying sizes. Okay, so that's all a lot of details in order to say that nanosynthesis is a different kind of activity than chemical synthesis. Like I said, most of the sort of classical chemical approach to synthesis happens in that first step, in that first beaker. And a lot of the problems that people are trying to solve in order to make nanosynthesis successful are problems that don't arise in the same way for regular old chemical synthesis. Now, a lot of them are using chemical techniques. Sometimes they're using physical techniques, but largely chemical techniques in order to solve these problems. But they're problems that are raised specifically by the nanoscale. There are a variety of chemical and physical strategies to solve them. Um, I want to pause and do the lecture version of a footnote here. So I'm talking about colloidal nanoparticle synthesis, which is done primarily on metals. There are a whole host of fabrication approaches in nanoscience. Many of them are less chemistry forward than colloidal synthesis, but colloidal synthesis is the more chemistry E1, and even here, it gets kind of unlike classical chemistry pretty quickly, which I just think is interesting. And the different strategies that are used in order to accommodate the special problems of nanoscale synthesis end up, this is a kind of practical aside, end up limiting the use of nanoparticles in various ways. So like I showed you in the quantum dot picture, the fuzzy white stuff on the outside of the quantum dot isn't part of the quantum dot, but it's going to interact with anything that's in the quantum dot's environment. And so it's going to limit the kinds of reactants that the quantum dot might interact with. It's going to limit the kinds of environments that you can put it in. So this is where I think that we might be able to inject some philosophy. All of these synthetic challenges affect the nature and structure of our knowledge about nanoparticles, even as they affect the way that we craft the nanoparticles themselves. So this is something that doesn't limit itself necessarily to nanosynthesis, but that I think is important in nano. The idea that when we are performing a synthesis, we are doing something that's knowledge making, and knowledge making perhaps in a different way than theorizing, than writing down a law of nature, than doing a detection experiment, but that is knowledge making nonetheless. And that, if we are kind of science forward, epistemology forward philosophers of physics, we want to be able to say what that knowledge making looks like. So this is actually giving away the ghost of the ultimate goal of the book is to kind of wind up in this claim that synthesis itself, I don't know how to make this this drawing go away, this annotation go away, so it's just going to be there forever now. So this is our sort of third option for discussion, to think about synthesis as an epistemic activity. And I'll say here that I think this is a more practical way of addressing the problem of intertheory relations than thinking about reduction and emergence. What I mean by that, intertheory relations are traditionally conceived within reduction and emergence in philosophy, but instead, we could think about intertheory coordination. So you saw it takes a lot of physics, a fair amount of chemistry, some quantum, some classical, in order to tell the story of how to make these nanoparticles. And in case I didn't make it clear, the big challenge that's facing quantum dots right now is making the dang things, right? Like, in order, we actually have a fairly good handle on the physics, the semiconductor physics of quantum confinement. Making the things, making them well, making them monodisperse, making them efficiently is the main limiting technological challenge for quantum dots right now. And that was the point of the chemistry review that got sent around to the summer school students. So my question is, like, what if we think about that problem as philosophers, and what if we think about it as an epistemic problem? If we do, then intertheory relations becomes a matter of justifying how we get these different models and theories to talk to one another in order to make the dang things, then as opposed to a story of like epistemic priority or metaphysical priority or what's really real underneath it all. And I've argued elsewhere, I have this conceptual strategies approach to multi-scale modeling, that conceptual strategies, which are just that's the term that I use for how we hook up a model or a theory to another model or a theory, that these things that we do require reasoning, produce new knowledge. So getting from the chemical synthesis into the phase change, getting into the models of growth from the chemical precursors, requires moving into a new kind of conceptual domain of how to think about the material differently. I think that produces new knowledge. this is still an argument that I'm like quite actively working on. And so it's something that I'd be happy to discuss in our discussion section. I want to just emphasize that when we apply this set of ideas to synthesis, we get an approach to intertheory relations that rationalizes the claim that synthesis is knowledge generating, or what I'm calling here an epistemic activity, which also gives us a solution. It's a solution to a different intertheory relations problem, but it's a solution that produces relevant strategies for scientists looking to solve synthetic challenges. If we, as the kind of people, philosophers, who are good at conceptual analysis, could help think through better how to connect up the pieces of synthesis and hand that off to the chemists who are trying to do the synthesis, then we've done philosophy of science in service of science. So that's discussion option 1. Discussion option 2 is this alloys stuff. So alloys, nanoscale alloy projects use mixed bulk and surface methods. We didn't really talk about that, but I'd be happy to talk about it more. Like I gestured at in the lecture, I'm really interested in how we make sense of the concept of an alloy in quantum dot synthesis, and how we sort of import and export the associated conceptualizations that go with macroscale alloying, like grain structure, like the process of annealing, which is some of that folding and heating and cooling that we do to change the grain structure of an alloy. Do we have analogs to that at the nanoscale? Does it help us make alloys better to hold on to that? Or should we ditch the idea of an alloy wholesale and just build a new theory from scratch at this point? So that's what we could talk about if we want to talk about alloys. Lastly, I've been kind of dancing around some of this reduction and emergence stuff. So we've been talking at the classical quantum interface. Those of you who were in the discussion group with me on Friday, I mentioned that I have some interest in intertheory relations that tends to be around the classical quantum interface. Some of it is, I think, content-wise specific to the classical quantum interface. Some of it is more general views about intertheory relations that could export to other areas of science. And one thing that came up in the discussion on Friday is the idea that, this is not necessarily opposed to reduction or emergence, but that I think both the questions of reduction and emergence are kind of the wrong questions to be asking when it comes to intertheory relations. So I saved this one for last, even though it kind of came up first in the lecture, because I was hoping that some of that stuff about synthesis would help show you the alternative that I'm thinking of. I want to paint you a quick reductionist picture of everything that I've said so far. So it's all about energy, right? Everything that I've said is about moving electrons around, which is just a way of moving energy around. And so all we're trying to do is conceptualize energy in the right way. And I think that's the wrong way of trying to resolve what's going on here conceptually. And I'm going to borrow from some folks in the last season of Parks and Recreation in order to show you why. So, of course, the point here is that you could reconceive of everything in terms of energy. Is that a good and useful way of telling the story that you're trying to tell about what's going on in the science? I don't think so in this case. And I think it's important to be able to tell the story of how we get quantum confinement out of bulk semiconductors in order to understand the physics that we're trying to build, and to tell the chemical story as well. So a more serious way of putting this point is that I think the success of semi-classical approaches, I haven't hammered on this vocabulary of semi-classical, but we see semi-classical approaches as the kind of watchword for a lot of the stuff that happens at the quantum classical interface that I've alluded to here, especially when it comes to electronics. So how can the success of semi-classical approaches challenge our conceptions of reduction and emergence as the relevant intertheory relations? And I think that some of the conceptual strategy stuff that I'm working on could be an alternative here. So that's the third discussion option. Now it is time to take a break and figure out what you want to discuss. I've shown you the three things that I think are kind of the big morals that are going to make up different chapters in the book project. And I'm also happy to talk about anything else that you want to talk about.
Yeah, so I think this is relevant to the chosen discussing topic. So yeah, I was just curious about, you know, maybe the inappropriateness of the sort of questions we ask when thinking about reduction and emergence, which is often posed as a question of inter-theory reduction, is inappropriate for discussion of chemical synthesis and what have you, because of these practical concerns. And yeah, so my question is something like, you know, I think we can usefully pay attention to the goals of the scientists in this case, and they clearly have a goal in mind, which is making their quantum dots as much like particles in a box as they can, getting these controllable splitting energy levels. So it seems to me they're not really interested in theory building. What they're interested in is realizing in the world some sort of system that obeys the theoretical description. So it seems more like a case of Nancy Cartwright's nomological machines. They're trying to create these quantum dots which realize this, you know, fairly abstract description that we get from textbook quantum mechanics and control it. So yeah, I'm just wondering about this question of how your interests as a philosopher of nanoscience are diverging from those of more sort of traditional approaches to philosophy of science because of the approach that the scientists are taking. Namely, they have this goal in mind, and it's not a sort of pure knowledge goal. It is a practical technological goal.
Yeah. So I was totally with you until the very last sort of 8 words or so, where we distinguished between pure knowledge and technological goals. I think I think that's a distinction that very much exists within the history of philosophy of science, and that I don't want to be the primary distinction between what gets called sort of epistemically appropriate for us to analyze or not. I think that knowledge happens when we make things, and that a lot of knowledge, scientific knowledge, is built in the processes of synthesis, and that's part of what I was trying to convey in my discussion of the synthesis protocols, is that, like, I think that is as important as theorizing to making science happen. And it's important in a similar way, where without the synthetic protocols, you're not going to make the thing, just as much as without the particle in a box theory. If you like, particle in a box really isn't even a theory, right? It's a model of a particular result of quantum mechanics, and it's a like fully conceptual model itself. So without the particle in a box thing, you're not going to get there either. And I don't think, and I mean, this is still something that's very much sort of open and in the works as part of the book project, is like, my impulse is that there's not a kind of interesting distinction between the kinds of knowledge that are produced there. There are certainly different uses, different ways that they get sort of drawn into and codified as scientific knowledge, but I don't suspect that there's a difference in kind, where like theories are going to give you propositional knowledge and synthesis is not going to give you propositional knowledge, or, you know, some of the old school ways we might think about distinguishing types of knowledge. So let me rewind to some earlier parts of the question. First of all, God, I love this application of nomological machines to what's going on with nanoparticles as trying to build particle in a box. I love it, especially because, so Cartwright's just published this series of lectures, the Keras lectures, where she's redescribed nomological machines as mechanisms, and it broke my heart because I love nomological machines, and I think the mechanisms literature is so muddy and loses so much of what she gets out of that way of understanding knowledge through modeling. So I might use that as some ammo later on in the book. And thank you for that. So there was something else I wanted to say. Might relate to Jeremy's question about sort of bringing this into hacking world and experiment world. Can you remind me the central worry that you're poking at with reduction and emergence here?
Me?
Yeah.
Oh yeah. So just saying that there's a sort of, it seems like there's an implicit assumption in talking about reduction and emergence that we're not concerned with praxis and synthesis and so on.
Good. Yes. Okay. Perfect. That was exactly the reminder I needed. So yeah, reduction comes from intertheory reduction historically. Absolutely. In more recent years, and I think this is partly the way that the philosophical discussion on modeling has gone in the past 15 years or so, and also just some of the sloppiness in distinguishing between models and theories that folks like Hacking and Cartwright pointed out to us in the 80s. You see moves between intertheory reduction and multi-scale modeling starting to crop up in the last 15 years, but especially in the last like 5 or 10 years. And when I say you see, I mean, I'm very much part of this move, this impulse to look to multi-scale modeling as an alternative framework for understanding connections between pieces of science's knowledge base, whether it's theories, models, heuristics, experiments, what have you. I think the central underlying question behind reduction and emergence is like the really old unity of science. Like, how do all of these different sciences manage to be about one world, or do they, or is there one world underneath, right? That's the kind of metaphysical reading of it. The epistemological reading of it is like, how can we ever know anything? And when we know something, are we knowing something in chemistry? Are we knowing something that's in chemistry, but it's physical knowledge that's just getting sort of filtered through chemistry because it's more convenient for us cognitively. So, I think as you move both from the metaphysical motivation for answering the unity question to the epistemological motivation, but then also if you're looking at the really kind of foundational reduction and emergence question, we'll call it intertheory, intermodel relations question of like, how do all of these puzzle pieces fit together? I think the theory to model distinction starts to make less sense quickly. And then if you look into what's going on with modeling, like once people shut up a little bit about representation and got into the more interesting parts of what's going on with modeling, not just like, does this really represent the target system? And what does it mean to really represent? Like, this is very much not a principal distinction. This is just a personal interest distinction. I find that to be a less interesting part of the models conversation than the question of like, how do models manage to let us do things? Whether that thing is like bolster our confidence in a piece of theoretical knowledge or make a new material. So I actually think, I mean, you probably saw a bit of sloppiness in the way that I was talking about the difference between intertheory relations, intermodal relations, heuristic relations. And that's somewhat intentional. I mean, some of it is just because I talk quickly because I'm being interrupted. And some of it is because of projects in the early days, but some of it is because there's just not a strong distinction between those things in my head. And I want to keep it that way. And I think it's important we get something out of keeping it that way.
Cool. Sorry. I just muted it entirely the wrong time. And they just pointed out some background noise. Great, thank you. So yeah, I don't want to dominate discussion. Does anyone want to jump in? Jeremy, maybe?
Hi, sure. Julia, thanks so much for the talk. I was bringing up hacking's do we see through a microscope? I guess partly out of the thought that there might be something fruitful from that's intersecting with how you're talking about approaching the monodispersity problem as like an epistemic activity. Or at the very least that maybe it might serve as like a good contrast, right? Because a lot of I think there's a way of reading that piece where Hacking's pushing really what he's concerned about is an ontological question, right? Are we justified in redrawing the distinction between observable and unobservable entities at a certain point based on our use of electron microscopes, like the sort of microscope used to produce the images that you were showing of the different sizes of the atoms.
Do you want that image up again?
Yeah. So these were different sizes of clusters.
Yeah, different sizes and shapes.
Yeah.
Let me just do something real quick. I'm just gonna like make this the whole size of things. This is gonna be a messy slide, but it might help us as we're talking. Oh, no, hold on one second. Sorry. There we go. Okay, try that.
Yeah, awesome. Yeah. So I was. This is a long-winded way of just getting to. I was interested if how you would situate this, like in relation to the sorts of concerns that hacking is addressing.
Yeah. So, you know, I tend to agree with hacking that there's a point at which we don't need to make an inference in order to count something as an observation, right? And is it when we're at, and so Jeremy asked in the chat earlier, what does FESEM stand for? Field emission scanning electron microscopes. So these are images that are not produced by optical microscopy, right? These are all well below the optical resolution limit of microscopes. And so these are electron microscope images. You can see the scale bars down there. It starts at A with a micrometer, 500 nanometers, 300 nanometers. Can you see my cursor? Is it moving? Okay, cool. 100, 100, right? And these are not quantum dots, to be clear. These are just noble metal nanoparticles that I grabbed because it was a convenient SEM image. Do I think we see these things? Well, I mean, on some level, I want to know why it matters, whether or not we do, right? And I think hacking, a different part of hacking, actually has a nice answer to this in his Homo Faber, right? So hacking famously has this line about we are Homo Faber, man the maker, and that's how that's the principle that we should use to develop our categories of knowledge. And so this is part of his argument for scientific kinds over natural kinds as the relevant criteria for building the categories of science. So when might it matter whether these things are observations or not? Well, you know, there are all of the boring ways where, like, if our microscope's acting up and if this is all an artifact of some, you know, some problem in the calibration, sure. More interesting ways, if it turns out that because this is an electron microscope and part of what we're doing is building things that are supposed to be giving us new ways of interacting with electrons, that like the microscope isn't the right kind of characterization instrument or detection instrument to tell us things about it. Like if there's a sort of, and this is totally hypothetical, just to be clear, hypothetical off the top of the dome, like if there were something that were happening with the way the electron gun was situated on the microscope, so like, you know, a scanning electron microscope is going to shoot a beam of electrons at this thing, and you get the image by the way that the electrons are deflected. You know, if there's something that's going on in the kinds of emissions that we are trying to induce in the particles that necessarily interferes with the detection mechanism, then we've got an interesting question about whether this is observation. But you're asking more generally, like, how does this line up with the stuff that hacking says about observation? And I think, again, my answer is going to be something along the lines of, yeah, I mean, I think there's some relevance in anytime we think about experiment, and especially experiment on things that are below the threshold or above the threshold or outside the threshold of regular naked eye human detection, even when they are condensed matter, then we've got some observation questions to answer. I think, you know, when I'm getting into the synthesis stuff, I don't think the observation question is the most interesting hacking question you could ask. And I think it is that kind of like man the maker, homo faber. How does the goal of making shape the categories that we're using to build out our models of them? But I mean, I've declared my preference for epistemology over metaphysics early and repeated it at least once or twice. And so someone who doesn't share that preference might see things that I don't in that question. And so I would be delighted if anyone wanted to jump in, because I've been doing quite a lot of talking.
Nick, could I follow up briefly, or do we want to jump?
Yeah, no, go ahead.
Oh, cool. Okay. Yeah. So just maybe to build on that a little bit, or maybe like sharpen what I was getting after. Would it be fair to say that? So I think like in the when hacking is talking about observation. Part of what he wants to do is associate observation with manipulability, possibly even like reduce observation. Yeah, if you want to take like a really strong reading, reduce it to manipulability, and then draw metaphysical consequences out of that. So would it be fair to say that like the approach you're taking here is sticking with assessing the consequences for manipulability, but sort of just remaining quiet on the ontological consequences?
So, I mean, this is actually, I like that rephrasing of it, because that poses a new and I think interesting problem of, you know, making isn't observation or manipulation necessarily, right? Like you can kind of see how manipulation leads to making a new thing, but the other hacking bumper sticker, if you can spray them, they exist, which is the, you know, his example of how we want to believe in electrons on the basis of being able to manipulate them. So do I want to remain quiet about the metaphysical consequences? There's one thing that I do think is an important metaphysical claim out of all of this, is that we sometimes make new things. And I think that I don't really know, and this is probably something I'm going to have to work out for the book, what the ontological implications of that are. because there are some, right? Of course, that by saying we sometimes make new things, and when we're making new kinds of nanoparticles, I actually want to go further and say not only are we making new things, we're making new kinds of things. Because I like making claims about classification, and they usually don't tend particularly metaphysical, but I think that there's no way to read that where it's not a metaphysical claim. And it also means that I have to have at least an ontology that permits new stuff to get added to it, right? The catalog of crap in the world is open and getting written in every day. And I do think that's right. And I don't know if there are any sort of non-cartoonish reductionist positions that would disagree with it. I mean, I think you can think of the cartoonish reduction position as like, well, all of the atoms in the world exist, and so you couldn't possibly be making anything new because you're not, like you're just rearranging things, and so they're new permutations, and this is, like I said, it's a cartoonish version. I don't expect anyone to actually hold this position.
Except
but,
Laplace.
Well, sure, yeah. But there's actually an insidiousness to that. Do I want to go on this tangent? This is going to be a hard tangent. Do we have burning questions? We're going to go fully out of physics for a second and into the pandemic. Okay, I'm going to do it. So I've been thinking about, there are calls for some like short pieces on historical and philosophical perspectives on the pandemic. And you guys can see, I think about nanoparticles. I don't really think about public health that often. But one thing that I have been thinking about a lot related to the pandemic, and this kind of gets back at some of the reduction and emergence orientations I have, is that we have a public image of science that comes filtered through the Laplacian demon perspective, the perspective that there is a perfect information out there and it's just a matter of accessing it, right? Exactly the perspective that Cartwright argues against back in the early 80s. And I actually think that image of science, however it's gotten transmitted into the public, has been really damaging to our ability to respond to the pandemic as a global population, because it's made everyone panic when there's not perfect information about the transmission of the disease, about the best options for safe protocols, like the likelihood of transmission, whether masks are good, whether it's 6 feet or 10 feet or 3 feet, who counts as, whose work needs to continue in order to carry forward the human race to get through to the other side of this, what's the likelihood of getting a vaccine. Like, we are used to, as a public, we trust science enough, and I don't want us to trust science any less. But the problem is, because the image of science that we trust is this perfect information image, the Laplacian demon image. I actually think we've done ourselves a disservice by expecting science to behave a way other than the way it behaves, by having a bad ontology of science that's led us to like additional anger and panic and confusion about the fact that there are multiple recommendations and the recommendations don't always align. Like, the expectation of immediate perfect information has made it a lot harder for people to reckon with changing advice. And of course, none of that gets into any of the, I think, more pressing and real political issues with communication of public health information. But that's end of tangent. But if anyone is interested in jumping in on tangent as well, I think there's a short bridge over to my views on reduction and emergence from perfect information is a bad assumption for science.
Yeah, Julie, I think I have a related question to this tangent and the ontic issue. And yeah, thanks so much for the talk. I'm sorry that I missed some of it. My internet kept cutting out. So I didn't hear everything. But so on this issue of requiring perfect information, to what extent are nanoscientists and the people like synthesizing quantum dots, for instance, to what extent are they interested in having something like an explanation for why a particular method might succeed? And I guess what I mean this in like kind of a practical journal context of like, when it comes to nanoscientist reviewers and they're writing an article and they've given some interpretation of the results, like, this is why I think this, technique succeeded, or like, this is why I think this technique worked better than this other one.
Right.
To what extent are the nanoscientists interested in like getting in the weeds about like, yeah, that's a good, interpretation of why that technique was successful versus, no, that's a terrible interpretation. You have the wrong model. Like, you shouldn't believe that. You should believe this other thing.
Right.
To what extent does that kind of like ontologically loaded, explanatory loaded discussion go on in the field?
Yeah, good question. So, and it's good to see you, Josh.
Yeah, good to see you too.
So, the boring answer is different people have different preferences, right? Like, some scientists just like getting sort of stuck in the weeds with that stuff, and some don't really have time for it. And I would say, in general, like 6 out of 10, if I were to kind of average over the nanoscientists that I've spent time with. And if you look at the way that papers are written, I think the Ella Visados review that I sent around to the summer school students, that's actually like it's a really nice indication of the general tone and tenor of how how nanoscientists tend to think about their attitudes with respect to explanation and ontology. And a lot of it comes back to exactly this question that Jeremy was asking about, like, how is this related to control, right? Atom by atom control is the ideal of nanoscience. I also think that's a bad ideal, right? And I'm saying it a little quietly because I get in fights with nanoscientists about this sometimes when, I try and tell them that, like, I don't think that's what you should be going for exactly this Laplacian demon reason, right? And we do have some ways of performing atom by atom control. I think I alluded to it briefly when I mentioned something about like moving atoms around with an AFM. An atomic force microscope, like you can in principle pick up an atom and move it around. And has anyone seen the Boy and His Atom IBM cartoon from ages ago? Okay, it's a great little cartoon. I'll send a link to it to Nick later. But it's a cartoon. It's a sort of stop motion cartoon that's made by moving individual atoms around on a template with an AFM. And it's a little boy and he bounces a ball and it spells out the IBM logo and it's cute. And it demonstrates atom by atom control. And a lot of nanoscientists, if they don't think about it too hard, think that what they're trying to do is atom by atom control. And then you start asking them about the implications of that, and it gets instrumentalist pretty quickly. Like if you push at least a lot of the chemists that I've pushed on it, they go from being kind of reductionist realists to, well, I'm just trying to do what works and I'm trying to make the thing. And if I make the thing, then that's what I need to do, pretty quickly. And they don't actually see a strong distinction between those two positions. And that might have influenced where I've landed and some of my own interests as well, because I think it probably isn't a surprise at this point to say that, like, I actually don't see a particularly strong distinction between those two positions either, except that I think the instrumentalist one is a bit more tenable. I've just realized I'm still sharing this image. I'm gonna stop so that I can see people a bit better. So the question of where do different nanoscientists locate themselves? Some of it is individual preferences, and you could do kind of like fun sociology on that. But I think it actually gets at this deeper question of like, what do nanoscientists conceive of as the aim of nanoscience? And so Josh knows, and I will share with the rest of you, when I was doing some of my early work in nanoscience, I worked in a lab of nanoscientists. And by worked in a lab, I don't mean I was like one of the people pouring the beakers of stuff into other stuff. I mean, I was going to group meetings every week and talking to them and asking them like weird philosophy questions, and sitting in lab and watching what they're doing and asking them why they're doing it, and generally annoying them. But annoying them in a productive philosophical way where we got at some of the messiness of the concepts that were at the heart of a lot of their activities. So alloys is one, surfaces is another that I've talked to death in other areas before. And the notion of synthesis itself is another one. And so this is one that came up in a conversation with the PI on the lab a year or two ago. And she and I were talking about exactly this problem that I put on the synthesis slide of like, it starts as colloidal synthesis, but it gets non-chemical pretty quickly. And especially in the way that we think about colloidal nanoparticles as nucleating out of a solution, right? They form these seeds out of a solution into a suspension or a colloid. That's inherently a phase change story. And so thinking of synthesis as a phase change is different than thinking of synthesis as a chemical reaction. And she at least is worried about that, and is worried about what that means for the possibilities and the limits of describing what it is to perform a nanosynthesis. So part of this too is related to attention in, maybe not even attention. There's a tension between wanting to share synthetic protocols and make them public for good academic reasons and wanting to keep them private for good industrial reasons. That's not the thing that I want to really get in at, though. Either way, whether you want to share it or not, being able to identify what the relevant parts of a synthesis are is an important and non-trivial problem in nanoscience. And you know, there's a sort of classic story from early nano days of someone submitting a journal article where they listed the rate at which they were stirring the material in solution as it grew. And this is the kind of thing you would just never put in an organic article. And it was kind of laughable. It was like the equivalent of saying I highlighted my article with an orange highlighter. Right? Like, it doesn't matter that it's an orange highlighter or a yellow highlighter. We never talk about methods in philosophy, and I think that's a problem, but like, you're not going to say in your methods, I went in and highlighted the article, period. But talking about stir rate as an important part of the synthesis is now fully standard in nanoscience. And it's because of all of the problems of keeping things within that tight growth regime that I was talking about on the slide. And so, you know, I think there are still real stories to tell about what counts as the parts of synthesis. And that's the kind of thing that I think that I want to be able to capture in the idea that synthesis is an epistemic activity, that is something that both requires modeling, but then also produces new knowledge, right? Like, it is a new propositional fact in the world that, I mean, maybe it's not a new fact depending on how you think facts work, but it's a propositional fact that the stir rate affects nanosynthesis in a way that it doesn't affect organic synthesis. And that's something that we learn through synthesis. That's knowledge that's produced through synthesis, and it's not super theoretical. I mean, you can give a theoretical justification to it down the line if you want. Some people do, some people don't. I think I've gone on a number of tangents now, so I'm hoping some of them have piqued other folks' interest. Or maybe, Josh, if you have responses that you want to give.
Oh, no, I'm happy to hold off responses for other people's questions. Otherwise, yeah, I guess I'll ask a follow-up. So there was this really interesting series of sentences at the end of the draft paper you sent around on quantum dots, where I think the content was something like, it's very important to view these growth models and these techniques for limiting growth as being in some kind of like interacting relationship with one another. And I guess I was wondering how you see this approach to the conceptual strategies, like viewing the techniques as interacting with the models. How does this connect with like traditional distinctions between like theory and experiment, or traditional distinction between like prediction and confirmation? Like the model makes some kind of prediction and then the technique confirms or disconfirms the prediction of the model. Are those older categories still useful, or do you think there's a sense in which they need to be rewritten or like radically transformed to make sense of this kind of synthetic process?
Yeah, I think this actually comes back around to the point Jeremy was making about the observation manipulation question, where I want to say that synthesis is a kind of third category or nth category there, where it's not the same as mere manipulation, it's not the same as observation, it's not the same as theorizing. And so I'll be honest, like that interacting model stuff and the models of growth is actually pieces of my dissertation that I haven't found a home for anywhere else. And that's part of the reason that I want to write a book, is because I feel like there are places where I want to get in the weeds with the science in a way that it doesn't make sense to in journal articles. And so the idea of models of growth interacting gets really mixed results. Like people either connect with the idea that models can interact with one another to like generate new knowledge very immediately, or they're like, what could you possibly mean, right? There are category mistakes that you're using there. And so I'm interested in how it's landing for the folks who are hearing it here, and especially for those of you who did get a chance to read through the reading and want to send me notes about it afterward. This is still something that I'm struggling with, whether that's the right way of describing it. You know, I have a colleague in philosophy of biology who's picked up on the interacting models language when she talks about different models of the heart, mechanistic models and sort of functional models, and more like fluid dynamics models of blood flow in the heart. And so it at least works there. And I think it's an instance of this more general approach to a kind of bottom-up answer to the foundational inter-epistemic object relations of, you know, how are we getting these different models to talk to one another to produce a new fact or a new ability in the world. I'm not sure that just saying that they interact tells us much. It might be the start of an answer, in the same way that those of you who were in the Friday discussion, like the Winsberg handshake is the start of an answer rather than the end of the answer, to connect it up to some of our earlier discussions. I feel like I'm talking around the question. Have I answered the question at all, Josh? I'm not sure. I feel like I went in a different direction.
I think, yeah, I guess to rephrase it, are you still happy to talk in terms of theory and experiment and prediction confirmation, or do you think those categories shouldn't be used that much in this context?
Good. So I don't mind if they're talked about. I don't think they're the way that we should talk about what especially these models of growth are doing for nanoscience. So what are the different models of growth doing? They're giving us different ways of conceiving of the problem of growth. So I would say, you know, in some of the language I've used before, they're invoking different conceptual strategies, right? It's not an observation or a detection. It's, you know, it's a how possibly model. It's a way of thinking about the moving parts of the system when, as I was alluding to earlier, like part of the challenge of nanosynthesis is identifying what are the relevant moving parts. and so the ways of thinking about how to limit growth, like sometimes they are really practical, just like what is the physical action you're taking in the lab? Are you going to dump a different solution into your beaker at this point? Are you going to change your stir rate? Are you going to introduce a capping agent? So like the white stuff on the outside of the quantum dot I was showing you, it's a capping agent, it's a surfactant, it's something that's supposed to help us inhibit growth. And there are different explanations for how it's inhibiting growth. Some of them are mutually compatible, some of them are not. Some of them will say, you know, what's happening here is you have these long ligands and they're interacting electrostatically, so they're preventing new atoms from coming in that way. Sometimes they'll say it's just it's a steric interaction, so just the physical bulk of the stuff is what's changing it. Some of them will say it's passivating the surface, making the surface atoms less energetic. Some of those are compatible with one another, some of them aren't. And I think it's a lot more important to the philosophers than to the scientists whether they're going to be like ultimately compatible in terms of the propositional claims they're making about the behavior of the material. The scientists, and this is going to come back all the way to your original question, Josh, like the scientists care about whether they can make the things and whether they can make the things well. And if it happens that having a better explanation of how the surfactant works makes them make them better, then great. That's when they're going to care about it. But I don't know quite what role detection or theory or experiment have to play in that story. Now, I will say that makes my job harder as a philosopher, because philosophers know how to tell stories about theory and observation and detection and experiment. We have that language built into our dialectic history, right? Conceptual strategies, that's mine, right? Like that's new and weird, and I have to explain it every time, and I kind of hope that people get what it means, and I don't expect that they do. So if you've heard me say it, 10 times and you're like, what the fuck is she talking about? You're probably not alone. And I'll be honest, some days I'm like, I don't really like, do I mean X or Y by this thing? And that's why the book hasn't been fully finished yet. I'm still trying to work it all out. So I think at some point, and this is where both Tom and Jeremy's questions were really helpful in directing me to like, what pieces of existing philosophy of science are getting triggered by this, by this discussion. So thinking about it in terms of Cartwright's nomological machines, in terms of both Hacking's notion of observation, his ontology, but then also his claims about kindhood. Those are all ways in to make this less of, both foreign philosophy and foreign science.
Cool. Thanks, Julie. Yeah, that completely answers the question.
Cool. Thank you.
So I see Tom has a hand, but I give priority to students if there is your chance to ask questions if there's somebody who'd like to. Okay. Well.
Yeah, so I had just about this last thought. So yeah, that paragraph opens with the claim that these models aren't guides to action, but they seem to be operating as a source of hypotheses, where the hypotheses are not sort of theoretical but practical. If I
you muted yourself,
Tom.
I'm unused to the spacebar technique, so keep the spacebar down. So yeah, so the hypothesis would be, increase the surface area, reduce the time or whatever, then I increase the yield of this process or something like that. I mean, is there more than that going on?
I think there might be less than that going on in certain cases, right? So like there's the like, let me just try this approach to experimental protocol. And so I think sometimes you're right that there are the sort of, you know, if I add this surfactant, it's going to change the surface area and that's all I need to know. So I'll go do that. But I also think there are times when, especially around nanosynthesis, it's like, let me just try this thing, see what happens, right? Where, you know, it's even less recipe driven, heuristic driven than just let me add surfactant A instead of surfactant B, or like higher concentration or lower concentration. The lab that I worked with in grad school actually had a name for this. It's the Friday afternoon experiment. When you're at the end of the work week, and this is not particular to them, but like this is a thing in science, the Friday afternoon experiment of just like, let me just go see what happens. And sometimes cool things happen and sometimes nothing happens. And part of the reason they happen on Friday afternoons in nanoscience is because a lot of times you need your particles to grow over the weekend. So you like go do your thing on Friday afternoon and you come in Monday morning and see what you've made. And I think this is part of the problem that I'm facing in trying to incorporate the idea that synthesis could be a knowledge forming activity into philosophy of science is this exact sort of question of like, well, we have maybe not good. We have categories for like what counts as knowledge in philosophy of science, and we've made arguments for what those categories are. And so like, if it's not any of those categories, show me what else it is, right? And like, I haven't done that in what I've presented today. I hope that's clear. If it wasn't clear, I will make it clear now. I don't think I've given you like knockdown arguments that there are new categories of knowledge, or that synthesis is giving you, you know, familiar categories of knowledge that are cleanly slotted into A and B and C. Like, this is theoretical, this is model driven, this is propositional, this is know-how. Know-how comes up, right? Like in the synthetic claim of things like this experimenter has good hands, you hear sometimes in chemistry, like they're good at getting the synthesis to go. And that's very much a tacit know-how, and you know, it's the kind of thing that is probably better explained by someone like Andy Clark than by like a philosopher of physics, where they're thinking about like the ways in which we tacitly know things. The big claim that I at least hope to have like given you some provocative food for thought on is that when we're making things, that generates knowledge. And it might generate knowledge as a byproduct, right? So if you want to go the more ontological route, if you're with me on the ontological claim that we sometimes make new stuff, and even that we make sometimes new kinds of stuff, well, there exists a new kind of thing in the world. That's the metaphysical claim. And then anything about the details of that is going to be kind of epistemic, right? Like we might want to know what kind of thing that is, what kind of properties it has, how those properties connect to the structure, how they connect to the process of making. And I think that's the kind of minimal claim that I want to ascribe to this idea that synthesis is an epistemic activity. I think there's a lot more to it as well, and that's why I've spent so much time with you all today. And I think part of what more there is to it is a redescription of the ways in which our models and theories and heuristics and even experiments all combine to spit out scientific knowledge. Some of that comes from reconceiving reduction and emergence as not about theories, but instead about models and heuristics and all of the epistemic objects that you might want to populate your scientific knowledge base with. I almost wonder if like old Kitcher language of explanatory stores or knowledge stores might be useful as a general category for like the big bucket of stuff that scientific knowledge is made of. But then also the idea that like within the philosophy of experiment, a lot of our philosophical writing on experiment comes from detection experiments, or characterization experiments, analytic experiments, as opposed to synthetic experiments. So like Hacking's Peggy gun, the Alan Franklin stuff on, oh my God, the peas, right? the Mendel-Fisher controversy. I'm now reaching like 6 years back in my reading history. So with apologies to Franklin if I'm getting it all wrong. But, those are still, the Mendel-Fisher, like growing the peas is an interesting one, because that actually, they did have to make new things for it. They had to make new pea pods. But the goal of that wasn't to show whether you could make new pea pods out of old pea pods. They knew how to do that. The goal was to show something about the kind of pea pod you're making. And just to make sure everyone's on board here, I'm talking about the old Mendel experiments about genetic descent, right? If someone has the details quickly at the ready and wants to do it, that'd be great. In the absence of that, I will say I'm pretty sure there was stuff about wrinkly and smooth pea pods and possibly yellow and green pea pods as well. And they were tracing whether if you started with wrinkly ones, you would end up with wrinkly ones. I'm not a biologist nor a philosopher of biology. That's about where my level of understanding of the Mendel experiments is after 2 hours of talking about nanoscience. So I'll leave that thought there. The point that I wanted to make with it was that the kinds of experiments, and that was an example of one of the kinds of experiments the philosopher talked about, the kinds of experiments that we have figured out how to decompose and analyze and conceptualize as philosophers are primarily analytic experiments where you're detecting something or characterizing something, determining the properties of a thing. Synthetic experiments aim at different things, and so it would be kind of weird if they just so happen to have exactly the same epistemic structure as analytic experiments. And a big part of the back half of the book is going to be trying to give a positive account of exactly this epistemology, right? Like what happens epistemically in a synthetic experiment. That's the question that I started with before I even got into nanoscience, like a decade ago now, and I still haven't answered it satisfactorily for myself. And so as I'm talking through these things, that's really underneath a lot of it.
Thanks. So if there's no one else, maybe I'll take up Keith's challenge. So, I mean, just a matter of personal history, ultimately, I'm interested in metaphysics. James Ladyman convinced me, he was my tutor at the time, that you need to be a good philosopher of physics in order to be a good metaphysician, naturalized metaphysics and all that. And, roughly speaking, here I am doing philosophy of science. So a counterpoint or alternative view would be something like, philosophy of science is there in the service of philosophy, and so we should be looking to the the practice of physics by physicists as sources for our philosophy, say natural philosophy, traditional questions of natural philosophy having to do with space-time matter and so on. And I just note that, in terms sociologically, you can see there's a sort of split. I imagine you've been keeping up your attendance at Philosophy of Science in Practice. I've been going to Society for Metaphysics of Science. These are two entities.
Mm-hmm.
I mean, my view of SMS is that it's sort of metaphysicians trying to cozy up to philosophy of physics, philosophers of physics, philosophers of science. And I'm guessing that, philosophy of science in practice is philosophers of science trying to cozy up to scientists, if you will. So there's the sort of sociological observation. I mean, philosophically, I think epistemology should be in the service of metaphysics, at least for the sort of questions that I'm interested in.
Mm-hmm. Yeah, so I'm so glad you wanted to take this back up. I think I'm gonna put this motivation screen back up just for kicks to give you all something else to stare at. It might also be worth sharing that Tom and I have known each other for probably 12 years now, and I think the first 4 or 5 of them, it was us trying to figure out that we are on opposite sides of like what we're doing in philosophy of science. And it's funny because we're both, I think, much more into the history than certain philosophers of physics and have spent more time doing serious history scholarship, but with these distinct motivations. So as I said at the beginning, and here, I'll grab my cursor, right? I like doing philosophy of science for science. I like to think of philosophy of science as a service discipline to the sciences, at least as much as it is part of philosophy. This gets me in not trouble with my philosophy colleagues, but it gives me less to say to some of the folks in my philosophy department here in Kentucky than I have to say to some of the folks in biology or chemistry or physics departments at the university, just in terms of what's going on with my research, right? And that makes a different way of doing philosophy. I'm so glad that you articulated so clearly. I do think with Tom that like metaphysics, philosophy of physics as a foundation for metaphysics is A, the right way to do metaphysics, and B, one of the ways that knowledge of physics can best serve philosophy. I'm not sure that having a bunch of knowledge about nanoscience ultimately serves philosophy in any particular way other than giving me an extremely complicated and overwrought set of arguments against this Laplacian demon view of scientific knowledge, right? And like, I don't need them, right? Like, A, Nancy Cartwright probably did a good enough job back in 1977. And B, no one's gonna have the patience to sit through all of this nano stuff. My analytic metaphysician colleague doesn't need it in order to make her claims about the ways that parts of the world hang together. So it's a separate fight, like whether one should be on my side of things or Tom's side of things. And it doesn't need to be a fight, right? Like I think there's room for both, and there's also room for folks at the interface who are doing a bit of each and looking for ways that metaphysical claims do constrain and limit the kinds of epistemic claims that one can make, and they do. And similarly, the kinds of epistemic claims that we make, I think, constrain some of our metaphysics as well, right? So perhaps I'll give one more shot at trying to open this up to the students of the summer school, since it's been a lot of us old farts talking. Now that you've sat through 4 weeks of this, do you have an impulse toward one way of doing it or the other? And we'll just we'll call them the Tom way or the Julia way for now. Like, or like what questions do you have about how these two different approaches to why one might want to do philosophy of physics in the first place, how those different approaches cause different challenges, both like philosophical challenges and personal challenges, because there are both of them on both sides as well.
Sadly, someone just unexpectedly started doing construction next door, and I missed basically all of what Tom had just said. Is there a way, Tom, you can succinctly give me the gist of it?
Sure. The much more succinct version is in doing philosophy of science for science, I think that's the reason that I end up with this priority toward epistemology. Tom gave a really nice characterization of an alternative way of doing philosophy of physics, which is to use physics to do scientifically responsible metaphysics in order to better serve philosophy by sort of building out metaphysical claims, ontological claims that are consistent with physics, with our best understanding of physics. And so the question to the group is, now that you've sat through 4 weeks of a philosophy of physics summer school, does one or the other of those sound like something you want to do or something you don't want to do? Or are there other questions that those of us who've been doing this for a while might want to answer, might be able to answer, that would help you figure out whether there's one side or the other that works better for you?
So can I say, I'm gonna jump to discussion. Yeah, thanks first for the talk. I enjoyed the talk and all the discussions in the last 30 minutes. Actually, what I'm gonna say, I think is related to what you just asked, but in some ways relates to other things that Tom and others said before, Josh. I think, I mean, I'm not sure, this is not exactly a question, it's like kind of like a question, kind of like a comment, but in my experience, at least like as a graduate student, I have seen a lot of times different types of attitude towards metaphysics, towards philosophy of science, in a way that I think it's been kind of, in some way it could be divisive. Like I have noticed, for example, like, I mean, everybody knows this, like people saying, oh, analytic metaphysics is dumb. They are talking about these things that have no contact whatsoever with the sciences. That's one very extreme side of the spectrum. Then there is the other spectrum of metaphysicians attacking philosophers of science for not being clear, like when using some concepts or like using loose ideas from metaphysics in a non-rigorous way. And at the end, like there are philosophers of science fighting with philosophers of physics. So I feel like part of what I'm trying to say is that in a way, this attempt to say why we should do metaphysics or why we should do philosophy of physics could lead in a dangerous path in which you try to say this is the justification for doing what you are doing, instead of just saying like, you know what, do what you like and enjoy it and try to do as much as you can, and then you can try to take a step back and see how it connects with other things. But yeah, like trying to get very rigorous answers to why you should do this in this way or another, in my experience, that have been kind of problematic, because I see this fight between different groups, different communities that I don't think is very productive at the end of the day for anybody. So, I mean, this is not like a response or anything. It's just like a thing I have experienced, and I've noticed that the profession in some ways goes in this direction. And yeah, so I want to hear your views about this, like this general thought that I just said. Yeah. If you have any comments about that. Yeah.
Yeah, so sorry, I'm trying to Nick sent something from the YouTube chat as well. I'm trying to figure out if there's an optimal order to answer things in. Let me stick with this thread for now. Part of the reason I was framing it as like, is there one side or the other that works for you, is because I wanted more of the students to talk. And I was hoping by being intentionally provocative, I might get some of you all to say things. part of it is that when we are looking outward, either to scientists, to other philosophers, to other humanists, and trying to tell the kind of complicated story of what it is that philosophy of physics does and is to the world, the story that I'm going to tell is different than the story that Tom's going to tell, just in terms of like what our research is doing for larger sort of academic or intellectual purposes. And you know, I was framing this as one side or the other. I'm not sure that that's, you know, that's optimal as a, because it breeds, you know, it breeds this sort of combativeness, which I'm not actually trying to invoke here. What I do want is more opportunities for people to talk about why philosophy of physics is a thing worth doing. And I think that, you know, as we are reckoning with a new academia in the 21st century, and those of you who are in the summer school are probably trying to be part of that new academia, like we're going to have to tell stories about what we're doing and why. And the days of being able to just be left alone in your office to write about some stuff and see what happens, you know, I'm not sure that those days ever existed. I don't think they existed for people like me, by which I mean women doing philosophy of physics, right? Like I've been on a constant path to justify what I'm doing since I began this whole process, and some of that is gendered, some of it is not. I'm not really looking to get into the details of that, but I think, you know, I do often find myself trying to justify why I'm staying in a subdiscipline of philosophy that has so few other women, when there are other subdisciplines of philosophy where I might find a more even playing field. And some of it relates actually to this YouTube chat question of like, why am I talking about chemical techniques for quantum dots rather than physical production methods for quantum dots? And the answer to that is the same as the answer to why I've stayed in philosophy of physics. It's because I like them, right? I like chemical techniques. I like colloidal techniques. So to the person from YouTube, the reason that I started with quantum dots is in order to introduce a combination of physical and chemical concerns. So there are physical concerns in terms of producing and tuning the semiconductor effects, the quantum confinement effects. And in at least the Elevisatos review that the summer school students were reading, they're looking at real chemical challenges. And chemical means of producing quantum dots are, in principle, significantly cheaper and require less ultra-high vacuum than certain physical means. They are behind physical means in certain other ways, which is part of why the synthetic challenges are so interesting and pressing scientifically. And I think that's interesting. And I like thinking about it. And I spent a lot of time thinking about it. And this is getting a little bit at what Sebastian's comment started with, which is just like, can't we all just like what we like? And the answer is sure, but I think it's useful to understand why you like what you like and frame the way that you like the things you like against what the other person or what an other person is doing, especially when you claim, you know, like Tom and I are both philosophers of physics. We show up at a lot of the same conferences and some different ones. But being able to say how our two research programs relate to one another, I think strengthens the field by showing the different things you can do with philosophy of physics. And you can only do that if you have a clear account of what it is you're doing and perhaps a comparative account of what someone else is doing. I will also say extremely practically, like I've been in grant writing mode for most of the summer. And so some of my views on the importance of justifying why I'm doing what I'm doing to a non-specialist audience might be heightened by recent writing experiences.
Yeah, just a very short comment on that. And just to clarify, I am on board with, I think, everything you just said. I was not questioning you, asking us why or what can we do and why, but I was just saying sometimes I have seen these questions with a different purpose, the purpose of like defending yourself, and like in a way kind of that seems like kind of aggressive maybe, or like just like trying to challenge you to show there is value in what you do. And sometimes given that story is not straightforward to someone from either a different field within philosophy of physics, or a different field within philosophy, or even a different field in academia. So that's what's my comment about, like sometimes this ask for justifying yourself reads like what you do is not valuable unless you can give me this story. And that's the part that I like struggle more with. Yeah, just to clarify that. Yeah.
No one else is going to jump in. I just wanted to make a brief comment to the effect that this inequality of epistemology and metaphysics would have been endorsed on Julia's side by most of the people whom we consider the founders of the field. It's a bit of a historical quirk that it's okay to do philosophy of science and metaphysics. 50 years ago, or at least 60 years ago, that was not the case. So it's worth just noting that we come out of a tradition which really did value epistemology over metaphysics.
Well, and I also think, Tom, you have a harder job in certain other ways where like contemporary analytic metaphysics has a real tense relationship with the sciences in a way that like I don't sort of know the details of it the way you do. So this is partly an invitation for you to talk a bit more about it. But, you know, I have a colleague who's an analytic metaphysician, and we talk sometimes about research, and she has a very different need for science, or belief in like how much of the details of science are going to serve her philosophical claims and serve her research projects than someone like you, where like as you were explaining, right, you think that getting into the details of physics is really going to solve a lot of the metaphysics, and I agree with you on that fully, right? And I'm quite happy to let you go work out the details.
Or at least complicate.
Right. But so, you know, I think you're between, you know, a Scylla and a Charybdis a bit on both the philosophy of science side and the metaphysics side, where there are metaphysicians who will say you don't need that much science, and there are folks like me who will say you don't need that much metaphysics. Is that accurate? I mean,
yeah, I mean, it's also the case with journal editors. You know, send the same piece to a few different journals, and it'll come back too much physics, too much metaphysics, depending on the journal.
Yeah. Oh, and similarly, right? Like I get the comment all the time. Where's the philosophy in this, right? Like you've just done the science. Where's the philosophy? Or alternatively, I'll get the metaphysics reviewer who thinks that my claims are about an ontology when they're not, and especially because I use very old school language of talking about concepts, right? The concept of a surface, the concept of an alloy. I still have this paper that was one of my favorite papers that I've ever written, all about the concept of a surface, and every time it gets sent out for review, like the thing, I sent it out for review for the first time in 2014. I still haven't gotten it published. And every time it gets sent out, like someone gets it, and then someone is like, you're making a bunch of metaphysical claims about reduction that aren't consistent and that need Descartes or don't need Descartes, or you know, or it gets read by different people in different ways. It's fascinating sociologically and annoying from a professional development standpoint.
What I've misunderstood, I think, could be summed up with the question, like, isn't epistemology and metaphysics a little bit zero sum? Like, the stronger our epistemology, or the better we think we understand that, isn't it? The less, the less sophisticated our metaphysics need to be, or the other way around, where we can like discard metaphysics just to take like the most elaborate epistemology possible. Do you think that's true or no?
I like the language of mutual constraint when I'm talking about, and I didn't bring this up in the talk today, but I like to use mutual constraining in order to talk about how different models interact with one another, how different, in some of the computer simulation of nanoscale cracks that I've analyzed, or talk about how there are mathematical choices that constrain but don't dictate the way that you're going to apply a model. There are physical choices that constrain but don't dictate the way you're going to apply a model. I actually think you can take that same language of constraining but not dictating as what I genuinely take to be the appropriate relationship between metaphysics and epistemology. They do mutually constrain one another, but I think the times you get in trouble are when you think that your metaphysics should dictate your epistemology, or that your epistemology should dictate your metaphysics. And I'd be happy to continue talking about the relationship between metaphysics and epistemology over lunch, as it seems we should probably wrap up.
Yeah, it's about 12, so I don't know. I mean, some people probably have to go, and I didn't want them to kind of miss anything. So, and also give them the chance to say thank you.